Let's look at weak acid equilibrium. It's a little bit more complicated than if you have a strong acid or strong base. First of all, the general equation, we see that we have dissociation of the weak acid into its ions. Remember that it strongly favors the reactant side, and so these end up having equilibrium constants that are less than 1. The equilibrium constant for acids is called the Ka. It's the acid dissociation constant. And it's done the exact same way, products on top divided by reactants. And I have two types of equations here, one that uses that hydrogen ion and one that uses the hydronium. But either way, it's going to look exactly the same. So one's going to look like this, and then the second one, instead of having the hydrogen ion, I would have the hydronium. Remember, you do not put water in your equilibrium constant, so that's why you're always going to have two products on top and one reactant on the bottom, and it will always look this way. There are different types of weak acids. So one type is the ones that are not the strong acids. So any sort of acid that is not one of those 6 that we memorize, it will be at equilibrium. So this one is hydrofluoric acid, and we can dissociate it into its ions. This second one, this is acetic acid, and by the way, you do not need to know the names. So this is an organic acid, and so the hydrogen that's here at the end, that is the H plus that will come loose, and then I have my acetate ion or my conjugate base. And then this is nitrous acid, and again that hydrogen ion comes off. The other type of weak acid equilibrium equations that you might see are conjugate acids of weak bases, but these are going to do the same thing. So an H and a plus is going to come off of it, and then you'll have your leftover. Later on, when we talk about salts, we'll also talk about very positive cations can form acids or weak acids. One thing with all of these that makes this a little bit more complicated is you need to use an ice chart, because these weak acids only dissociate a little bit. So to figure out the equilibrium and the equilibrium constant, then we typically do an ice chart. When we write dissociation equations for a strong acid, it dissociates completely, and we don't really use Ka acid dissociation constants for strong acids, and that is because this right here at the bottom is essentially 0. So in that 0, this ends up being just a very, very large number because it only has products. If we have weak acids, then these acid dissociation constants, they're important because they help us to show how much is dissociating, and it helps us figure out the pH and the pOH and things like that. So in this weak acid, I just take off a hydrogen, and it is at equilibrium, so I would need that backward arrow. And then we just have products divided by reactants. Just some more examples. So I'm going to pull off this hydrogen, and then my acetate ion will be negative. Products on the top, reactants on the bottom. And let's do our next example. So when I take away the H and take away the positive, then my conjugate base is neutral. Again, products on the top, reactants on the bottom. And in all of these, because they're weak acids, my Ka is going to be much less than 1. So I'd have to be given information on the concentration, or maybe I'd be given information about the pH, and that would help me to solve for this problem. Let's go ahead and do an acid dissociation problem. This says lactic acid is a waste product that accumulates in muscle tissue during exertion, leading to pain and a feeling of fatigue. In a 0.1 molar aqueous solution, lactic acid is 3.7% dissociated. Calculate the value of Ka for this acid. So I'm going to write my dissociation equation, and it's just right here. And I'm going to do an ice chart. So I have initial concentrations, my change, and then my equilibrium. And remember, it's this last row, the equilibrium, is what I'm going to put into my Ka equation. I can write my Ka equation. And let's fill out our ice chart. So initially I have a concentration of 0.1, and these are going to be 0. I'm going to lose a little bit here, and I'm going to gain a little bit here. Now notice when in my balanced equation, it's a 1 to 1 to 1. When you're doing these acid problems, they're always going to be 1 to 1 to 1. So for acids, there will never be a 1 to 2 relationship. So I'm going to pull this down. I'm going to get 0.1 minus x. and this is going to be X, and this is going to be X. So very typical ice box equation. I am given some extra information. This says 3.7% dissociated. And when I look at my hydrogen ion versus my conjugate base ion, I see that they're always going to be the same number. And this actually is telling me what that hydrogen ion concentration is. Now for this problem, I am given some extra information, and it's this 3% dissociation. There's a little formula, which is percent is equal to that hydrogen ion concentration divided by the molarity times 100. So I know what the molarity is, I know what the percent is, so I can solve for that hydrogen ion concentration. So let's put in what we know. When I work out the math, I find out that my hydrogen ion concentration is equal to 0.0037. So that essentially is what X is. So I can go back into my ice box and I can put in what X is. So every time there is an X, I'm going to put in this number. I can simplify this 0.1 minus 0.0037 and I get 0.0963. So I can take the ones on this bottom and I can put it into my formula here. So my final answer, I get 1.4 times 10 to the minus 4 as my Ka. Remember, there's no units. So a few things that to notice about acid equilibria. So this is a problem. If we're given the percent dissociation, we can use it to solve for that hydrogen ion concentration. So let's do another weak acid equilibrium problem. So this one is HF. So this is a weak acid. It's not one of our strongs. I can write the dissociation equation, and I already wrote it down here where our icebox is. We can write the Ka expression, and then I can put in what I know. I know that my concentration is 0.5, and at the beginning I don't have any of this, and then I'm going to lose some of my reactants and gain some of my product. And pulling everything down, I get 0.5 minus X, and these are both X. I do know my Ka, it's given to me, and I can fill in what I know. I could put X times X or X squared here. Remember, for acid equilibrium, those two values are always going to be the same. I'm going to have to use the quadratic formula to solve for this, and the AP board will never require you to use that, so we're going to take the shortcut. We're going to say that X is tiny, so we're just going to get rid of it. So I'm just going to have X squared divided by 0.5. So simplifying this, I'm going to have X squared equal to 3.6 times 10 to the minus 4. And then I'm going to square root both of these. And my X is going to be equal to 1.9 times 10 to the minus 3. And what is X? X is that hydrogen ion. So from this, it wants the pH. So I'm going to take the pH by taking the negative log of that hydrogen ion. And my final answer is 1.72 is my pH. So I just want to double check that it does come out to be an acid, as I know that it is a weak acid, so I should have a pH that's less than 7. I can double check that it was okay to take the shortcut, and I can do this by finding the percent dissociation. The percent dissociation is equal to the hydrogen ion divided by the molarity times 100. And so when I work this out and put in what I know, the hydrogen ion and the molarity, I get my percent as 3.8%. And so the rule is, as long as you're less than 5% dissociation, then you're going to be okay. We have a 3.8, and so it's going to be okay. Sometimes we are given a mixture of weak acids and we need to determine the hydrogen ion concentration or the pH. You will also be given the Ka values for those weak acids, and so you need to decide how are you going to find that hydrogen ion or the pH. And you're going to use the one that has the highest Ka. So in this example here, I have hydrocyanic acid and I have nitrous acid, and both my Kas are given there. So I'm comparing a 10 to the minus 10 and a 10 to the minus 4. The 10 to the minus 4 is the largest, And so that is going to contribute to the most hydrogen ion. This hydrocyanic acid is pretty weak. It's almost close to water. So remember, water's Ka or Kw, it would be 10 to the minus 14. The water and the hydrocyanic acid are not going to contribute much to the hydrogen ion concentration. Instead, we're going to focus on this nitrous acid. So we're first going to write the reaction, and then we are going to solve the ice chart with the information that we've been given. I start out with a concentration of 5 and nothing over here, and then everything's a 1-to-1 ratio with these acid problems. So this is what I'm going to put into my formula. I am going to assume that my minus x is tiny, so I don't have to do the quadratic equation. There's my acid dissociation constant. Let's put in what we know. And when I square each side, I find that x is 0.0447. So this is what the concentration of the hydrogen ion is. And so then I can find the pH. And I find my pH is 1.35. We can double check that it was okay to take the shortcut. So I do this by finding the percent ionization. So let me plug my numbers in. And then I have a 0.894% ionization. That is well below the 5%. So it was just fine to take this shortcut. So there's our pH, 1.35. We've been finding the Ka, but weak bases also have a base dissociation constant. The general equation is you take the base plus the water, and then the water is going to donate a hydrogen ion to the base, and so you end up producing this OH in solution. What is a weak base? Oftentimes they are compounds that have nitrogen in them, so they will have an atom that has a lone pair that can accept that hydrogen. So in my ammonia molecule right here, there's a lone pair, so when the hydrogen ion comes in, that's where it attaches. So let's just write out some equations here. So my ammonia, when put into water, it will be a reversible reaction, but I will make this ammonium ion. So it gets a hydrogen and a plus from the water. And then the leftover is the OH minus. And so that is what's making it a base, is that OH that comes from the water. We can do it with this next one, and it's going to be very similar. And again, the reason why it's a base is because it produces that OH. Other things that are weak bases are anions that are conjugate bases of weak acids. Remember, if you have a weak acid, that means that the conjugate base is stronger. And so this is a reaction that will occur. So it rips a hydrogen ion away from the water and producing that OH. So F minus is the conjugate base of the weak acid HF. And again, it will produce that hydroxide ion in solution. And then we have the conjugate base of this hydrocyanic acid. And so that Cn minus, it will pull a hydrogen ion off of water, and it will make this hydroxide. So in all of these, because they're bases, we're not going to find the Ka, we're going to find the Kb. And it's done the same way, but you want to make sure that you're starting with an equation that is showing that it's acting like a base. So in this problem, we want to calculate the pH of a 15 molarity solution of ammonia. And there's our Kb. And so we're going to write the dissociation equation, and we're going to do an ice chart. So start with what I know. So I have a 15 molar solution at the beginning. H2O is a water molecule, and so it does not figure out in our equilibrium at all. This is going to lose a little bit, and these are both going to gain some. And I'm going to end up with 15 minus x here, and an x, and an x. I'm going to assume that the dissociation is very, very tiny, so I don't have to do the quadratic equation. And then let's write our Kb equation. Remember, don't put water into this equation. Put in what I know. So I know my Kb, and I have x squared divided by that 15. Let's go ahead and simplify. And then I'm going to square root both sides. And I get 0.0164 as my x, and this is my OH. So I'm going to find the POH first. And my POH is 1.78. But we want the pH, so I'm going to subtract this from 14, and I get 12.22. We can just double check that it was okay that we assumed that X was tiny. And so I'm going to do my percent equation. And instead of doing the hydrogen ion, I'm going to do the hydroxide ion this time because this is a base. And I get a 0.1% dissociation. So this is okay that we took the shortcut. So some difficulties with this problem, just remember that when you have a base, you are going to have the water as a reactant, most likely. And so don't include the water in your ice chart or in your Kb expression. Just as another reminder, the stronger your base, the weaker the conjugate acid. And so when we are dealing with these weak acids and bases, if we end up having a stronger conjugate base, this will drive the reaction backwards. And so we are going to end up with very, very little products. And those stronger conjugate bases and stronger conjugate acids, again, would be a driving force of the reaction. Now, how are Ka and Kb related? They are related in this way. If you multiply them together, they will equal the Kw. So therefore, if you know one of them, you can calculate the other. Because I always know that my Kw is 1 times 10 to the minus 14. So if I'm given a Ka, I can find the Kb. If I'm given the Kb, I can find the Ka.